The course of today. So, how will it work today? I work today. First, we'll see about real, actual resource allocation problem and how does it really work, and try to give you a perspective of, yes, it's nice to do theory, but actually, you have to understand that if you want to go through deployment, what I present to you so far is actually not enough. And there is a lot of challenges there. And we'll discuss a bit about the different challenges and the different methodology. Then you will realize pretty fast that actually everything is complex in the deployment. And actually, you will try to make it simple, but in the worst case scenario, what can happen is that you're obliged to do some kind of reinforcement learning algorithm. I would not recommend that. It's kind of the worst things that can happen because the systems are too complex, so most likely it will not work. And I will explain you why. But still, after this introduction to machine learning for resource allocation for deployments, I will teach you a bit about reinforcement learning and especially deep reinforcement learning. And finally, for the lab, so the lab right now are more about, I will just share with you some code that you can play around with it. So there is two labs. One is how to learn. You have a queuing system, the ones that we have implemented so far. Are you able to learn using a neural network the probability to go from one state to another state? So basically, you are trying to learn the density, the distribution. And you will realize that actually it's hard. So it's easy to learn when you know the queuing parameter, right? You just have one value to learn. But let's assume that you don't know what's happening in your system, and you just try to plug and to learn basically a distribution probability, but you will realize it's actually extremely cool. Okay? And then there is also code that I will release to you that have been done by some of my students, including Bishwa, for deep Q learning, for machine reparation. And then you can just also use it on your framework if you want and try to extend it. Okay? And then, of course, we will work a bit on your project. But you have also, I think, to practice a bit the lab. It's important, such that you can ask me some questions about it. Okay, so let's start. So, of course, it's not. Okay, so a bit of context. What is a realistic telecommunication network? It's actually this entire system. You have a network with routers and switch, and you have traffic coming. You have multiple types of traffic. You have voice, video, data traffic. And basically, this traffic wants to go from a source there and going out to the network, right? And you, as the control designer, how do you control the network, actually? You send, you open your terminal and you send some configuration. Right? I want to apply this, this policy at the level of a queue, I want to have this routing matrix, and so on and so forth. We'll see a bit more in detail. And what you can observe, and I'm saying that it's not obliged, but hopefully you have some kind of per flow metric performance, which usually are about queue utilization, delay, loss, and link utilization. So what I would recommend to you for you to really understand what are the challenges of working with real deployment of network. So there is a challenge done by the Center of Networking of Barcelona, where they always, every year, they ask, can we try to learn? In some sense, the challenge is always about, I give you a configuration, I give you a network, I give you some traffic. Can we predict the average performance metric? And what they release two things all the time, even three things this year. And you can look at the past year. I put the links there. They release a simulator of networks done on OSNet, okay? So basically, everything is coded, and you just have to change the configuration of your network, and it will generate this. They also release a graph neural networks that have been trained on it, such that you can also, in some sense, if the graph neural network is good to study it, what you can just do is take the graph neural network and play with it, right? To generate some data. It will not scale, but you know. And the last thing is they are also releasing some real data sets. You know, real data set where basically they've created a test bed at home and generated some traffic. So the problem there is actually everything is hard. There is not a piece of things which is easy there in network. I would just, even before talking to you about the general issue, for someone who is deploying, why people don't use so easily machine learning these days in network? They used to predict, but you know, everyone is speaking, especially if you work in a resource allocation, about kind of smart networks that are self-healing network and so on, that are able to re-update themselves and so on. Why do you think it's not? It's extremely simple. Even if they mean that people actually are starting to kind of do an API on that, the devices are not even speaking the same language. If they are not coming from the same company, or if they are not exactly developed the same year, they don't speak the same language. So what's happening is just a mess to control everything. So one of the big jobs of you know, of this aggregate of network company, telecom network company, is to discuss with each other and to say, okay, now it's time that we're able to create a common language to control all our devices. And when there is a new coming in the market, he has to meet some standard. Okay, so this is one of the first challenges, is just controlling diversity of objects is actually not easy at all. You don't have the kind of backend to do it, right? And the other thing, which is kind of, I think, okay, this is another point, but let's move on to so please try to remember that we have three kind of classical parts in the network. You have the traffic, basically the packet entry with different characteristics. You have what you have, the configuration of your network, and you have the performance measure, right? It looks like a markup check. It's exactly looking like, but actually it is a bit more complicated. First problem is already coming from the input. Predicting traffic is just, and I will show you why. Another thing is just, again, controlling the network with configuration is easy when you implement your own test bed. But actually, when you are developing, sometimes, for example, so famous the big telecom operator in France is Orange. And you know, sometimes they use Cisco switches and so on. And so what's happening is the software use is proprietary. And what does it mean? It means that they give you a set of configuration, but you actually don't know what's happening in the controller. So you don't, it's kind of a black box. You have a set of rules, but you don't know what's happening. So this is just hard. So we cannot control as much as we want. And also, actually, you have, I don't know how many combination of configuration possible. So the action space is huge. And the size of the queue, sometimes it's not known, sometimes it's known. Most of the time it's not known. The routing path cannot be exact because you have some load balancing that you are not aware of, and so on. And every time you are trying to get some information a bit more about the system, for example, trying to learn the length of the queue, trying to be able to really understand the routing path, two things will happen. First, it requires a lot of engineering work that an engineer will do to make it happen. And this engineering work can switch from one system to another. And the other thing is that you add load in your network by measuring. Not too much, but at some point you have load because you need to send specific packets to measure the size of the queues and so on. So one thing that, because I'm coming from a network team management, even if I'm management in networking. So even if I'm more from the theoretical side, what I've learned working with this team is there is not a big problem in networking. Why? Because every system is different and has its own characteristics. So there is not a global solution. So the people that do research in networking management, so meaning that they really try to solve realistic problems in this setup, are obliged to restrict themselves to specific problems because you cannot just switch. Okay. So one of these conclusions also that I would like you to understand before I move to a bit showing you the difficulty is please don't tell that you have a solution that can go in deployment. This is false. And if you see that the maths that you are doing are not giving you a simple solution, it's not a good sign, right? Because imagine that you have to solve an LP with, I don't know, 50,000 constraints, right? And you're black and you are not able to do it. And just this LP, imagine, is just a vision of an idealist vision of the world, right? And then you have also to plug it in something which is not reliable, or basically not even close. So I think there is no problem in saying I'm studying this toy problem to explore it, but please don't tell that you are doing deployment because you are not doing it. Because deployment is manipulating configuration and things like that. And it's actually, okay, it's not the same job. Okay. So why traffic is hard to predict? So this is different trace of traffic. And for example, this is traffic inter-data center. And this, you can see that inter-data center, you have some kind of periodicity happening. So in some sense, you are like, okay, there is a lot of noise, but something can happen and I can predict. This is the customer-facing traffic. You know, you have your data center and what is sending the customer throughout the week. Well, you clearly understand that in terms of prediction, nothing is happening and you just need something which is kind of being able to tell you, okay, well, it's there, you know, and so on. So you see already the input is there. Okay. So when you come to see me telling me, yes, I have an MM1Q with Poisson arrival and so on. Yeah. Good for you, but actually this is your problem. The traffic is less. Okay. So you should read this paper because what I like about it is they do resource allocation for wide area network. And they really, basically, they have taken the engineering point of view, and this is what we'll see today. Basically, a part of my talk is based on that. But the goal is to show you that they have simplified as much as possible because, they're already facing this issue. So what is the configuration in it? What is your actual? So you can control the topology as a designer. You can control the routing, You can control link capacity. So this is actually what people in the, when they deploy power grid, when they deploy, roads and so on. Actually, the people in operation research solve this really complex integer programming to decide what is the topology and what is the link capacity. So this is problem on itself. And then in routing, you can decide the different protocols, right? And all these protocols will imply different stuff in your network, and you are not exactly sure of what's happening. Then you have your scheduling policies that everyone is clear about. And you can decide kind of the buffers, the kind of policies that you are using to schedule, and sometimes you have a hierarchy of policy if you have priorities and so on. And then you have other stuff, right? But basically, what you give, as a network manager is all this kind of stuff when you deploy your networks. And what is really nice when you go to these kind of challenges is they have coded for you the simulator, and you can actually play with all this. You can change the routing, you can change the traffic, you can change everything, and just look at the input and look at the output of your. Okay, so I find it quite nice. So now I think all of you have understand that resource allocation is hard. And now let's see how people This is a 2022. It was the best paper is Usenix, how do you say? Yeah. And you will see how people have really forget about everything that we have learned in the past week, and they have just made it simple and so on. Yeah. So let's say that we have a network which is modeled as a graph with capacities on each edge, right? Classical problem. And you say that you have tunnels, and each source vertex communicate with each destination T. You have a set of network paths or tunnels. So basically, there is a routing matrix for every source destination. If I want to go from this source to this destination, I have a set of paths that I can take. Okay. And you have this for every source and destination. Now you have a traffic demand, which is telling how much I want to send traffic from the source S to a destination T, and you have that for every node in the network. Okay. So what is the configuration there? The configuration are actually extremely easy. So for a given network and a given demand, the configuration specified for every coupled S and T, how much of the traffic incoming in S should be split amongst the different paths proposed in the routing matrix associated to the source S and the destinations. Okay, so you have a set of paths, you have a flow coming in S, and you have to say how much should I split? So I should send to pass 1, to pass 2, to pass 3, and I'm doing that for every source destination. Okay. Good. So the objective is to minimize the bottleneck. So basically, we want to minimize the maximum link utilization. In other words, we want to find the best, repartition, such as the link which has the maximum load, where the load is the number of flows going divided by its capacity, is minimum. Right. So you can see that it's actually pretty similar to what we have seen so far. However, there is no state. Right? It's just that we are doing the optimization. It's not a dynamical optimization. We are doing on the shot. So what it means is that they have completely forget about Q-lengths. They are saying that they are looking at the granularity where what is happening in the network at time t will not have impact at time t+1. Okay. So you could extend it to the case where there is an impact. There is a correlation, a temporal correlation, but we will then follow in our framework. And the problem is you will see that even this one can be harmed in some contexts. So this problem is a convex optimization problem and can actually be framed as an LP problem, right? And therefore, we have solver to do it. Okay. The problem is, there is an important input. You assume that you know the traffic demand, where actually when you, as a network manager, when traffic is coming, right? I actually don't know the exact demand during T and T+1. I don't have any clue, right? So I will fix an allocation for a certain number of time, and I have to hope that I have a good prediction on it, right? So the problem is, it's a nice optimization problem, but I don't know TS. I can observe it afterwards, but before I don't know it. So I do a decision before observing it. So how to handle it? So you need a model. And these people in this paper have kind of taken they were like, okay, it's hard, so let's take the worst models that we can take. And they say that the demand matrix DT is generating according to an unknown edge markup process with transition probabilities such as basically what's happening at instant T, the demand which is incoming at instant T, is depending on what's happening to T-1 up to T-H. So this is kind of the ARMA model. And why this model will work actually? It's because you have this periodicity, right? This periodicity will tell you that if you train it well, you know the moment you get something a bit down, you can guess that you are going down. The moment you reach a certain level, you know that you go up and so on. So this is why they have done this model, and what they have proved, at least on the data that they have used, that H is about level. Okay. And what they also assume in their model is that the Markov chain has reached its stationary regime, and this is standard assumption in time series analysis, because you don't want to learn something on the transient. So what is the first solution? And it's not the solution of the papers that I'm talking about. You first have a lot of domains. You know, you have all these curves that I showed, and you train something which is trying to predict the next domain. You put whatever neural network and so on. Predict what is the next domain. So then what you do, you predict what is the next domain, and you directly solve ULT. Okay. What is the problem? What is the advantage of that, and what is the problem? The advantage is what I like about training on a separate piece, your demand or traffic predictor. You can use it for other tasks. And actually, it's really important, right? You like to not have to train. So you can take this and use it for other tasks. And imagine that there is some problem somewhere. Perhaps you have missed something there and so on. Because you are using separate blocks, you can just study where the problem is by removing one block or another block. So it's really an engineering perspective that actually I will have to debug. And therefore, I'm happy that everything is a bit separate because it's easy to check. The disadvantage is because the predictor domain is used to predict the domain and not optimize. It's not tuned for optimizing correctly the frontier declaration. So if we try to learn in average all the domain, and it will not focus on, for example, if you know that this link has a small capacity, but you're obliged to go through it, you will be careful to predict really well your domains that are going through this link to make sure that you are not taking error, right? So this is one of the disadvantages. And the authors in the paper, but I don't agree completely with them, say so. The best thing is just to optimize everything at a go. So you give a demand, and then you try to optimize the configuration because you will get the demand after. So instead of trying to predict the demand, you try to just optimize the configuration depending on the past traffic condition. What is the big disadvantage is when there is a problem, you don't understand what's happening because everything is gone. So just also, as practitioner, be a bit careful with this elegant and nice approach that says that they can do everything. In practice, in theory, they can do everything, but then again, the moment you do deployment, it's going really bad when there is a deployment. Okay. So what is the algorithm that they have done? It's a simple gradient descent algorithm. So you have your neural network, right? And you have some initial parameters of your neural network. What you will do is you observe your past domain and you predict what is the next. No, sorry. And you observe your past domain and you predict what is the next allocation. You will say, this is the way I'm allocating my traffic, even I don't see the domain. Then I observe the actual domain, and therefore I can calculate how good was my allocation with respect to the domains that I did not observe. So I can compute a gradient because this, when you use automatic differentiation neural network, is just for free. And then you update your gradient. So it's what is kind of beautiful there. Okay, So I've talked about like the big words, neural network, neural network, neural networks, but I didn't even introduce to you what it is. But I will still avoid it because I think I don't want to go in this thing. You have layers, you have data coming, then you backpropagate. I will not talk about backpropagation and so on. There is enough content online, and during the lab we will learn about it. But I will, because I have a taste for theory, I've shown you an algorithm that works. Right? Now I will tell you about what can we say about neural network, and especially kind of the first theories that have emerged about neural network. And this is, some people have used this theory to do some analysis on neural networks. So there is more recent one, but this one is kind of the baby steps, the baby version that it can be used. Okay. So perhaps I can stop there. Is there any question about this problem? No. Do you realize that there is no states except the event? And that actually this is even that it's making it not so easy to solve, right? So this is the way you should do if you work with data, real data, forget about queues, forget about state, just first start to solve a simple optimization problem of this form. The moment you're able to do it, you can think of adding a state. But before that, just forget about it, it could just be too hard. And also, kind of a strategy when you do machine learning and do this deployment stuff is always to start really small. If you can ask to some of my students that are in the room that works actually on reinforcement learning in queuing system, so the moment you try to tackle the even just 10 queues, scheduling of 10 queues, you are just not able to do it, right? So you really have to fine-tune on a really, really small toy example your problem. 3 queues with a buffer of size to something ridiculous. And then you can think of scale, right? And this is really a trick to kind of progress a bit rapidly in the neural networks. And department. Never go for the big problem. Okay. So what about neural networks? So I will talk about something fun that I find really fun, which is called random neural network or random features. Let's say that you have a probability distribution on omega, and V, which is basically depending on an input, which is X, and some variable omega, which is belonging, which are distributed accordingly. And what you assume is basically V is bounded. It's okay, it's just kind of that. And what we will define is the following space. Let's perhaps look at this one. This is the space of function, which are linear combination of an input X, right? So f of X, and with some different parameter theta k, right? And this, you can see that basically you are studying the function which can be decomposed in a base of size k with parameter theta, okay? And you have some constraints about your weight. You cannot combine them everywhere. So norm one of every of your weights is a constant. The equivalent in the continuous space, and you will understand why, is this one, right? This is a real basis. Right now it's just for specific theta k, but for every theta k, it's a set of functions that can be approximated by this set of bases. Is this way. So what is this interpretation of this condition? It's just to make sure that we don't go too far in terms of, we kind of introduce some kind of sparsity. And what we say is that the distribution, the weight alpha theta, so the way I can combine my function phi, is decaying more rapidly than my given distribution p theta, right? So means that at the end, what will happen is I want that I'm in a restricted space there, so that it's kind of easy to know. So now let's study this beautiful theorem. You take any function in f, which has this form. So you can prove, for example, that every continuous Lipschitz every continuous differential function can be approximated by this type of function. Right here, there is always existence. That says that you take a function and you sample theta 1 and theta k according to p in a ID fashion, right? And you sample k of them. Then for all delta, there exists with a probability 1 minus delta, a function f hat in this set, such that you are pretty close to the functions that you. This is what means this one. So it's square root of k, is the number of samples. So what is it saying? It's saying basically sample randomly your weights, right? Sample randomly your weights. So, and you have k combination, linear combination. You sample one time, you sample k times randomly your weights. Then you do a linear combination. And there always exists some weights which will approximate well a function in this space. Okay, and this is the bound. So actually, what does it mean? What is the strategy? Is you take a neural network, all the weight except the last layer, sample everything randomly a certain number of times, and basically you are constructing what we call a random basis. And it's giving you a basis for free, right? And then you can just work on it, and you know that it has some kind of good performance. So the problem there is why it's not working, because you have square root of k, which makes it that it's working in 1 dimension, in 2 dimensions. But after that, you need the power of really neural networks to make it happen. But still, it's something fun to always try, because when it works, you have a direct theoretical. So for the people that have done a bit of Fourier transform, opera, compressed sensing. So basically, we just have created a basis to represent our function, but we have created it in a random way. And what we say is my basis is just a random network, a neural network. And for example, this is time series of delays in networks. So this is big data that one of my PhD students is working with. And we just are taking a small neural network, and we have sampled 20 times, and we have created a basis of size 20. And each time we have performed new experiments, and these are the results. So you can see that sometimes it's not working. Yes. And the number of points, we are not trying to fit everything. The number of points that we have sampled to train the neural network is 20 over 100. So you see that I'm completely down something by signal. Of course, the signal is pretty stationary. So as long as I'm getting a bit point here, a bit point here, and a bit point here, it's good. But just to show you that actually, as long as you are, the problem here is not the fact that we don't have a good basis, it's more that we didn't sample at the right places in the data. And it's kind of working. So this is just to show you a nice theory of neural networks. Okay. Okay, so now let's go back to open problem on network. So in the previous algorithms that I've shown, you need to know, you don't know the domain, but you know the capacity of the domain. Do you know that it's easy? Do you think it's easy to estimate the capacity of the domain? It's just a story. I think it's one of the, if I'm not wrong, it's a huge challenge, right, to understand the capacity. No, Marina? Or the Q-lens for sure.
If it's a DCM problem, no, otherwise it will matter.
Well, okay. So perhaps if you are proprietary of the networks and you kind of know, but yeah. And the question is, assuming that basically there is some stuff that you don't know in the network, how can you compute even the gradient? Right? Because you need to do a gradient. Actually, so we will see a solution. It's kind of easy. I will show it on the board. Now, this is the second big thing. What I told you is train your network on a small example to make it work and scale it, right? Because actually, well, this is actually the real challenge. How to scale. And I will tell you kind of the fundamental law that you should respect. There is some kind of, we know how networks scale, but still it's really hard. And then imagine that you start to look at the evolution of queues and things like that, the way we have done it so far. Then you are in reinforcement learning, and then in some sense you are in the sense that I think for me, the moment you hit the kind of reinforcement learning problem, if you are not ultra smart, perhaps you will be able to make it work on a small instance, but you will never be able to say. Except if you need to solve big challenges in the reinforcement learning. So what I'm also trying to say is reinforcement learning is not the answer at all to everything. Actually, it's quite the opposite. It's better to do what we have done in the past class, build an heuristic which is false, because not realistic with the assumption, but at least giving something controllable, scalable, and perhaps you can show that your network is still doing a bit better, because actually you don't care about optimality, you just want to do better compared to the current configuration. Or study if you don't have, find a way to not have state evolving, and just solve with this kind of gradient descent, because gradient, we know that it works. Okay. So imagine that, let's talk about gradient descent. How to compute a gradient. And let's imagine, so I want an algorithm that is doing that, right? But imagine that actually, at each time, I'm only observing y of n is equal to f of xn plus epsilon. What should I do to estimate the gradient? Let's say it is x is of what is a scalar. So remember the formula of the gradient. In case when it's a scalar, you know that f prime of xn is simply equal to limit of delta going to 0 of xn plus delta minus f xn minus delta divided by 2 delta. It's another formulation of the gradient, right? Let's forget about this limit. So the first thing that you could do is at each time step, you play xn plus delta. You imagine that you have an interval of 1 hour. The first half an hour, you play xn plus delta. You take what is the maximum link utilization in your network. And then the rest of the half an hour, you do the repartition, which is corresponding to f of xn minus delta, right? And just by doing that, what's happening is you have an estimate of your gradient, and then you can do the other steps. The problem is when it's multidimensional, you have to do 2 at the power the number of your division estimation, so it's just not possible. So people have come with some stochastic scheme. So basically, you have to look at gradient estimation. I have some paper on that also, but simultaneous perturbation scheme, where basically you toss a coin, and with a probability 1/2, you play xn plus delta, and with a probability 1/2, you play xn minus delta. And when you do that, in average, actually, if you divide by delta, and if you use as an estimator f of x, f what you play divided by delta, you will get the true estimator of your gradient. And you can basically expand this rule in a more complex setup by basically playing a bit randomly around your decision. So usually you take a direction in a unit sphere, and by doing that, we'll be always able to estimate a graph. So if you're interested, I can give you the reference. But what I'm trying to say is not knowing all the parameters of the network is okay. We know how to handle that. Actually, this one is not the challenge. The only thing is perhaps we'll have a lot of variance. It will take time to converge, which is another problem. Okay, so now let's go to the big problem. This is something that I'm trying to look at. I have this problem in mind since 1 year, but I've put some students on it, but still it's a hard problem. We have not came up with a concrete answer yet. How to transfer a network to another setup? What you have to understand is what does it mean transferring, and especially what is the notion of scaling. Imagine that you train on a small data set and you want to deploy on a big data set, on a big network. So you have to understand what is kind of the relation between a big data set, your big network, and your small network. And this is what I call the notion of scaling. Because imagine that you train, so let's even take the simple example. You try to find a scheduling policy of 5 queues. How to transfer it to a network of 100 parallel queues. And what's happening is you have to understand whether or not they are close to each other in some sense. And close doesn't mean that actually they have the same parameter, right? Perhaps they don't have the same parameters, you need to have different buffer size and so on to be able to really understand the scaling law. So this is really the notion of scaling needs to be understood, and it's not clear at all what it is. Even in the simple setup of queues, I don't have any clue actually. And what you have to understand is that it's not just, as I say, increasing the number of queues or just increasing the topology. Especially in networks, you will have two main properties that are kind of transferred. If you have a bigger network, usually bigger networks do not mean that you have a network which is spread. It means that you have the core network, which is getting bigger and more concentrated, and you have more edges around it. This is how networks are actually been like that. You have these core networks, right, where everything is happening. And then you have kind of the edge there. And when the network is increasing, so you will have more mass here and here and here, but they will not connect with each other. It's just becoming a tree. Imagine that you are building more houses. They are not connecting with each other. It's just another branch. And then the core is getting bigger and bigger to be able to sustain the load. So when I say bigger and bigger, it's in two things. One thing is it's concentrating more here. And there's another thing is the capacity are of course increasing. Otherwise, it's not possible because the traffic is scaling, is increasing of n, so your capacity, in some sense, are also increasing. So this is one kind of flow that you have to see. And also, the delay, some metric going in the network are actually also scaling, right? Because the shortest paths are kind of getting longer. When I'm saying kind of getting longer, when you design a network and you increase the network, you are kind of making sure that you don't have too many hoops. But still, because you have more flows going in and so on, basically, it will take more time. But typically, I think you had this example in Bangalore 20 years back. It was kind of a small city, not too many people, and then CCIT came in. Bangalore was not able to sustain the charge. So you have basically think of the growth of a city like Bangalore to understand the scaling law of a network. Just that the problem that at Bangalore was not able to extend its capacity because the rate was too fast. It's kind of in every traffic all the time. And then imagine that the challenge that I say that your network is changing over time. For example, if you want to put a control at the level of queues, then you're obliged to go to DPI. Okay. So that's over for the first part of my talk, which is, so I'm sorry if I was kind of not too specific, but really, it's really important that when we speak about deployment and real world problem, it's kind of the way it is, right? I try to give you the big picture and the big guidelines to work on them. If you want to play with some data sets, you can just look at all this competition and even participate to it. So what they do there, it's not about estimating traffic, they try to estimate the state of the network, right? So imagine you have a queuing network. Can you estimate, and you have a routing topology and you have traffic, can you find a way to estimate all the relevant metric? Right, so basically, in all the things that we have done, in some sense, trying to estimate the Markov chain. And the best things that they have come up so far is what we call graph neural network. And what is nice is it works when you change the policy, the scheduling policy means that it works for different type of configuration and so on. And there's already a solution, so for you, I think it's nice to just take this and play with it if you want. It's kind of a free lunch. So the problems that I thought about minimizing the maximum link utilization is coming from this recent paper from Usenix, which was best paper last year. And it's a really nice paper about how to really apply a resource allocation with big data sets. And now what I will do for the rest of the class, perhaps I will not take 1 hour, I will take half an hour to talk about MDP. But we'll do a small webinar of 5 minutes. Okay.
Yeah.
I'm just checking that okay. So now we talk about EQN. So you know this kind of things that goes on in reinforcement learning. So recently there is some work that saying it's not the best one and so on and so forth. What I would just suggest is very simple and it's kind of the way to start with. I've also given the book. So yeah. Alors. So let's make some brief recall on MDP and talk about dynamic programming and then so let's say that you have a markup chain. Xn on a finite state space. Yes, so I'm obliged to ignore everything, be sure that everyone is on the same page. And control by a control U of n on a finite state space, which live on the finite state. Action set on finite space. A. Okay. And what you assume is that because you have the Markov property, right? That xn plus 1 equal y, knowing xn and un, n smaller is equal to n, is just equal to the probability of xn plus 1 equal y, knowing just the last state and the last one. What we are interested is in minimizing the expectation, so finding the sequence of control UN such that we minimize, this time we will go to infinity, but with a discount rate, gamma n, of the reward function and of the control. Okay. So you have a reward which is depending on your state and your action, and you want to maximize the discount. Okay. What is the sequence of control to do that? So this is the general framework, and this is usually the one that is taught when you study for the first time in. Okay. So now we define the value function, which is kind of the most important thing here. That is the following. It is p of x, which is equal to the maximum of the expectation for given policy pi. So I've not defined pi, but now all of you know what is a policy. It is a mapping that take a state and give you an action, right? Maximum of a pi of the expectation of sum of n equals 0 to infinity of gamma n Rn xn to n, knowing that x0 is equal to x. So basically, the value function of x is the maximum when you fix the initial condition. Okay? I'm sorry, I didn't put the line. I will do. Okay. So, and the famous dynamic programming equation is telling us the following. I will not do the proof. It's the following. P of x is equal to the max in A of R x A plus basically the transition P of y knowing x and A, and I will explain this, multiplied by B1. So this probability is it's a probability of transition, and we will denote it P of y knowing xn and un. Right. So this is my poetic transition. And basically, the Bellman equation is simply telling me the following. My value function, so the optimal solution that I'm getting when I'm starting at x is equal to the maximum of my current reward at x when I'm the maximum when I'm optimizing A at the current reward, plus the probability that I'm going to another state and the value function of this other state. Right? And the entire goal of deep reinforcement learning, or all the reinforcement learning, all the reinforcement learning literature, is to find this thing for every x. So the goal is how to compute V, where V is actually, so I will just write it again here. So what you see is actually it's a fixed point equation. So one thing that you can see why it's feasible is let's fix A, right? So if I fix A, what's happening? I have B x, which is equal to R x A. So let's just even okay. What's happening when I remove this max? Can someone tell me how to find B? If I remove the max, what's happening when I remove the max? So let's say that I will just use equivalence notation. If I remove the max, this I will call it xi for some reason, we'll understand later on, is equal to yi plus gamma summation of j of pij y xj, right? So this is equivalent if I remove the max, and if I say that p of x is equal to xi. So I'm basically just doing a simple math. So this is just a linear equation for x. So the way of solving that, if you don't have a max, is just inverse the matrix. Okay. So just inverse the matrix. What I'm trying to say, if you fix a policy to know the value function, just inverse the matrix. It's easy. All the problem is in this max operator. So first thing to note is that V of X is a contraction. For the infinite norm. What does it mean? It means that the infinite norm of V of X minus V of Y is smaller in infinity than, I think, gamma of X minus Y in infinity, with gamma which is always 0, 1. So what does it mean? It means that using the fixed point theorem, it means that first of all, there is a unique solution to this fixed point equation, and also there is a stupid algorithm to solve this problem. And the stupid algorithm is called value iteration. You just, for every n, you do Vn of x is equal, and for every I, for every n, and for every x, what you do is you say that Vn plus 1 of x is equal to the max of A of R x A plus gamma summation of the y of P y knowing x A multiplied by the n of y. So basically what you do, you just recursively update your estimation of. So I'm taking the previous estimation of V, I'm plugging it on the right side of my value iteration algorithm, and then I'm getting a new one, and I'm doing that multiple times, and so on and so forth. And because it's a contraction, we know it's contraction. Does everyone who knows that already? And you just raise your hand. Okay, beautiful. So this is something pretty standard.
Sir, can you repeat how it is converging?
Why it's converging?
Yeah.
So just plug V of nx here. And because you have a contraction argument, the max, the norm inf is basically a norm max. So this you will not care. And just it's direct from there, actually. You will just have a recursion argument and you will see that it's a contraction. That's it. I will honestly I don't want to do the proof, but why? Because also it's trivial. You do an induction argument, you plug V and X here, V and XY. What you have to do is that you have to do something like that. V of nx minus V of x. And you know, there is this classical theory that say, let's say that T of x is a contraction. If T of x is a contraction, so this is what we teach in first year in math, actually. If T of x is a contraction, then it means that T of x minus T of y is smaller than alpha x minus y for some given norm with alpha in 0, 1. And then what you can just prove is that xn plus 1 is equal of T of xn plus 1 of T of xn, you just iterate, will converge to the right place. And it's called the contraction, it's called the fixed point theorem. It's something pretty standard. So the fixed point theorem is just telling you that there is a unique point, and this algorithm is converged. It's giving that hope.
And you are saying that we have to invert the matrix. So we are thinking that all things are matrix is invertible.
Really good point. So I say that if they were not the max operator, just inverse the matrix. And you say you are putting a good point. And why it's invertible is because of the gamma. The gamma is between 0 and 1. So what it will naturally do, it will force to make it invertible because it will make it a contraction. You don't have gamma, you don't have the invertibility.
Yeah, that's okay.
So this is why people work a lot with discount MDP. It's just because the matter is. The moment you don't do finite horizon, the matter is that there is some kind of, you have to be a bit smart. And average cost, actually, everything's fine. Okay. Okay. So still, it's not right now. What is the assumption that we have is that we know the matrix, right? And so we are still not in a reinforcement learning setup. In a reinforcement learning setup, you observe the evolution of your state going from x to xn plus 1 and so on and so forth, right? And you observe your reward. You don't have any knowledge about your transition matrix. So one thing that is easy to note is if I define Q of XA, which is equal R of XA plus gamma summation over Y of my transition matrix in Y, what I can know over A. So what does it mean? It means that V of X is equal to max over A of Q of XA, right? So I can rewrite this function this function as max over A. Okay? And what is the good news? The good news is my transition matrix is outside now my max. And this was the main challenge. That's the first things when we want to have something outside because then it's making it easy to estimate. Okay. So this, for people that are not good with Q-learning but have heard about it, this is called the Q value. Yeah.
But have you written like max A, Q of X? It should be Y. Yes.
Okay, really good. So now we have a new fixed point equation. But we still don't know how to handle the fact that we don't know system. Okay. But then yesterday what we have seen is stochastic approximation. Stochastic approximation is basically telling me find a differential equation which is converging to the right place, and then find a way to make it noisy, and then you are done, right? So what should be the differential equation? Let's say that I'm defining the differential equation XA is equal to R of XA plus gamma summation of the Y of P Y XA multiplied by max of A Q of YA minus Q of X. What I've just done, right, is I've taken this term here, and because the differential equation, we know that it should converge where the derivative is 0. So when I take this here, it's equal to 0, and I just put the derivative. What I do, what we can prove is by the same kind of arguments, this is also converging to Q. This will converge at the right place. This differential equation will converge to this fixed point. We can prove it. And it's stable, attractive, you know, you have all the good things that we have seen yesterday. So now the question is how to make it as a stochastic approximation. Really good. So what is the stochastic approximation scheme in this case? I'm just doing a simple Euler discretization of my process. I'm putting a discrete step size. So this is just Euler discretization. And then we know that I have to put everything which is inside plus some numbers. So I'm writing it here. Can I erase? Yeah. You don't like? Okay. Oh. Well, let's look at approximation. Plus some noise that I will talk to you about. So now, what are the things that we observe in the reinforcement learning? We observe the reward, right? So what do we know at instant n when we have an observation? We observe the current state. So let me grab this. We observe what do we observe at every step? The reinforcement learning setup. At every time we observe xn and r of of an xn, then xn plus 1, and so on and so forth, right? So this is the setup of reinforcement. So when I look at this algorithm, in some sense, this I know. Q is an input, right? It's a Q value, so I'm controlling it. So the only thing that I don't know is this probability, right? So I need to find a good estimate of this. So what I need to find is how to estimate the summation of the y of p y knowing x n a n of the max of the a of q n of y y q a of the max. This is the only thing that actually I know, right? And I will give you a good estimator. A good estimator, let's say that I'm defining z of n plus 1, which is equal to max over a of q n of xn plus 1. If I'm taking this as an estimator, what's happening is that in expectation, Zn plus 1 knowing xn and an is equal to the summation of the y of p y xn an max over a of q n y y. So basically, Zn plus 1 is a good estimator of the only things that I didn't. And it's a really fun estimator because I don't even need to take into account anything related to probability transition. I'm just plugging the next steps. So does everyone is agreeing with that? I'm just waiting 2 minutes to judge your identification. Because I see a lot of people writing, so. So simple, right? I've taken I know right now you are learning how to design algorithms. So let me just recall you the different steps. I want to solve a fixed point equation. So this fixed point equation can even written like that. What I will do is I will put hats on the place that I want to solve. I want to solve a fixed point equation. Let's write a differential equation which is converging to this fixed point equation. But the easiest way is you replace the 0 by x dot, because it means that it will be at least a stationary point of your differential equation. Then write the earlier discretization of your differential equation and ask yourself, what do I observe and what do I not observe? What do I observe? I observe my reward and states. So it means that I'm stuck there. Then just create an unbiased estimator of the things that you don't know based on what you have observed. Even if you are so unbiased means that the expectation is exactly what you want. Imagine that you are not able to do that, but you're able to design a consistent estimator. A consistent estimator means that at infinity it will converge at the right place. It is working also. So the only job actually of someone who wants to use stochastic approximation as a practitioner is be able always to design good estimator based on the observation. The moment you do that, everything is working. So then the classical Q-learning scheme, of course, what I'm not telling you is that there is, of course, some details that I'm omitting because actually it's okay. Is your classical Q-learning scheme is the following. Case n plus 1 of x a is equal to k n plus 1 k n x a plus 1 over n plus 1. And I will call it c of n plus 1. And what I will say is the following. It's equal to 0 if x is different than xn and a is different than an, right? Why I'm doing that? Because I'm just saying that we don't have observation, so we should not update, right? And otherwise, it's simply equal to q of xn plus, sorry, r of xn a n plus gamma max over a of q of xn plus 1 a, so a prime, so it's a prime. Here it's a prime. Just minus q, so it's n of x a. Yeah. That's it. And this, by the construction that I've done, automatically will converge at the right place by the theory of stochastic approximation. So, Q-learning is a good scheme as long as the space is finite and as long as and the space is not good. But when you want to control a robot, the space is already too big. And therefore, this is how people have started building some kind of linear approximation of the Q-value function. At the end, they came up with DQN. And I will explain briefly what is DQN. Does anyone have some questions? I've lost everyone. Okay. So let us say that, my state space is so complex that it's really hard to understand what is Q and A, right? It's, it's X and A can be 1,000, 1,000, you don't know, right? So what people have done is instead of, they will say, we will approximate QA by theta, by neural network. In the simplest form, they will say that basically Q is equal to AX plus BA, and they will say that it exists A star and B star such that Q, the real Q value, is more or less close to AX plus B. Right. And in the neural network, you can imagine that it's even more complex, right? The question is how to determine A and B. So what we would like is actually that we find A star and B such that the right should be, the right one should be the one such that this equation is satisfied for all for all x and I. So if I'm able to find the parameterization of my Q-value function such that this equation is nearly close to 0 for every x and a, what it would mean, it would just mean that in some sense I have been close to solve the fixed point equation. This is what is just. So this is the principle of BQ. And therefore, what is the loss? How to do that? You will just take a mean square error. You will say, I want that for every observation that I want that to minimize this error. So be careful. Actually, be careful. Yeah, let's say the true error is this one. And you will right away understand what is the problem. There is two problems. And you want to minimize this error for every sentence. There is two problems there. One problem, so you will take the derivative theta of the error. Honestly, taking the derivative of the max inside the square plus that and so on, clearly you will have a problem. It will not go well. So first remark is people actually only take the derivative with respect to actually, so people do some kind of approximation version of the gradient in DQA. They don't take the exact derivative of the function, which is called the true error, the true Bellman error. They just take the derivative in this term. They never take the derivative in this term. So gradient only on this term. Why you do a gradient? Because you want to do a gradient descent on the parameter of your neural network. So basically, you will do a gradient descent to minimize this error. This is your job. This is DQM. However, this one is problematic, so you don't even take the gradient out. So this is the things that kind of people in machine learning do. Sometimes when they feel that the gradient will just perturbate everything, they don't even try to compute it. They fix it. So this is a bit weird, but they do. And the other things that people do, okay, and the other problems that you will have when you write the gradient is you have still this term, right, that you actually don't do, and you will have to estimate it. But this is not a problem, because when we take the gradient, actually we again do something less than it would. Okay. So I will not go more deeper in DQN. I just wanted to give you the broad picture that try to remember the following. You have value iteration. Value iteration is a good algorithm when you know the transition level. Then you have Q-learning. Q-learning is designed when you don't know the matrix, but you are still in finite space. How to construct the Q-learning algorithm? You have a fixed point to converge. Write the associative differential equation. Discretize the differential equation. Then find an unbiased estimator of the part that you don't know. What is DQN? Parameterize your Q value function by a data. For example, you say that it has this form. And try to minimize the error, such that your parameterized version of your Q function is close to be a solution of the fixed point equation. At the moment you have that, you can nearly design any type of stochastic approximation algorithm. And that's it. Okay. Okay. So what we will do now? So first, if you have questions, please you can ask. So does someone here has already implemented DQN in his life? Yeah. So if you are, can you tell us about, is it easy to make it work or not easy at all? Why? What is the trick that you have made it? Perhaps you can share with your colleagues.
When the action space is used again, then you follow.
Ah, because you have this max operator. It's a really good point. Imagine that the action space is huge. Then you have to solve this max operator, and a max operator in 2 to the power n is boring to solve, right? In our bandit problem, typically this is what will happen, and we don't know how to solve it. Okay. And what else?
Please will get I1 new environments. We don't know if it is because of the right architecture or the algorithm itself. So I mean,
okay. So the problem is again because you are trying to do a lot of things at the same time. When you will try to optimize your neural network, you don't even know if is it the algorithm which is not converging fast enough. What is the rate, or is it your neural network which is not expressive enough? And this is the classical stuff that are extremely boring to do when we do ML. And actually, one thing is to program really well and to just run a lot of experiments and then to pick the best. Okay. Okay. So there is 2 code. So there is a lab and then there is an exercise session as your project. I'm not sure. It would be nice if we can finish a bit. It has been a long week, I think, for all of us, including myself. And it would be nice if we can finish a bit early. I would like to finish at perhaps 12:45. So I would suggest the following. There is 2 labs, but the labs, everything is given, right? So there is a lab on how to use neural network to learn queuing systems. The length of a queue, the description of a queue, and there is a lab about how to implement DQN. And basically what I'm expecting from you is you have the code and play with it. Make it more complex architecture, adapt it to your problem, make it such that you can extend it in your case. So there is some advices, but just play around with it. And then there is your project. And with respect to your project, what we can do is I would like to still do the lab when I'm here because this is important. So we can do, let's say now, half an hour, 45 minutes of lab. We can take not half an hour break, but 15 minutes break. And then we do 45 minutes of projects. And anyway, I'm there during 1 month. You can just send me some mail about your projects, and I will reply to your emails. Okay, in case we are not able to concretize all your projects. The goal also of your project was not actually to solve really your resource allocation problem, is also to make you sense of it, how to make it fit to the framework. And I think now you have also. So perhaps we can do 15-minute breaks now, then we do the lab, and we will finish at 12:45.
So made at 11:05, yeah?